All right, so we're going to come in and we're going to do a summary of the last video that we did, which was on 6.3, where we were looking at our integrals, definite integrals, and the summation notation. So in general, the main idea that we have here is that you are going to need to be able to translate from your summation notation to the definite integrals and vice versa. So they may give you a definite integral and ask you what summation notation matches it, or they might give you a summation notation where you have the limit of a sum and ask which definite integral that you're going to have there. So let's take a look at the parts that we have down here. Now, kind of the main thing to remember as you're translating is that there are these formulas that you have to basically memorize, that you need to know that given that you have equal widths, okay, so assuming, I'm going to add this up here, assuming equal widths, then our delta x is always going to be b minus a over n, and then our right endpoints, which are the ones that are most likely to be used, are going to be this, I'm going to highlight the bottom one because that's the one that we see the most, where you start at the lower bound and you add your delta x times I, where I represents the number of rectangle, what rectangle number you're on. And remember, kind of as you're doing it, I is also the index on your summation notation. So over here in the what things are all equal to each other. So I'm going to highlight them. Your integral from a to b is this limit of a sum notation that we have. So that's this portion right here. The second thing that you look at is understanding that the delta x, the dx up here is the delta x, which matches those coming down through there. Now, obviously, your function, when you're taking a look at it, let's do blue, the generic function that you have, you should be able to pick that out of your kind of lineup of what function would you plug the right endpoint into. And then the right endpoint, go to green right here, is, by whatever name that you look at it, is something that you want to be able to match up. And so you want to be able to kind of move through each of these, and also this understanding that we are summing the area where what's here is always your height, and this is your width, and that when you multiply those together, that you are really adding up your areas. So we have an infinite sum of areas. Now, let's just kind of do a little side example over here before I basically set you off into doing your homework and doing a lot of practice on this. So the example I'm going to start with, so we're just going to kind of slide it in over here. So example 1, when you look at that, I'm going to give you the limit notation. So I'm going to give you the limit as n goes to infinity, sum I equals 1 to n of the square root of 5 times 2 plus 4 over ni minus 3 times 4 over n. All right, so now your job when you see something like this is to identify a and b, to identify what function you're dealing with, and rewrite this as an integral. Now, when you see this in the multiple choice, you immediately know that this is a definite integral because when you have the limit of a sum, so that's kind of your code that as you're starting this problem, this is going to be an integral. And we also know that when we are doing integrals, that the ending part of the integral is going to be, actually, let me color code this the way that I did before. So let me change my colors so I match. Part of my OCD over here. So here we go. So we have the limit is the definite integral. So this is going to be my definite integral. Now notice at this point I don't have the a and the b yet, but I will get those shortly. The other thing when you're taking a look at this is to understand that the dx is this portion over here. And remember that the dx is what's going to turn into that part of it. So we kind of put this in, and we put our integral symbol in. Now we have to do a little bit of work, because the work that we have to do is to understand we have to find a, b, and the function. So the first thing is I actually use the delta x. Once I have delta x is 4 over n, I'm going to remember that that's b minus a over n. So right now, we know that b minus a is equal to 4. The other thing that I am going to look at is what's inside of the function. So I'm trying to identify where the quote-unquote right endpoint is. And so we kind of look in here and we see that we have this expression inside of there that has the I. And so I'm going to identify that that's my right endpoint, 2 plus 4 over n times I. And when I look at that, remember, here's my delta x times I plus a. And so immediately what you're getting out of the identification of the right endpoint is I'm going to get to conclude that a is equal to 2 in this problem. And once I have a is 2, it's the combination of the b minus a equals 4 and a equals 2 that's going to allow you to conclude that b must be 6 in this problem. So we kind of utilize delta x and the right endpoint formula to match up and get our a and b. So here is my lower bound, and here is my upper bound. So I'm going to fill those in. So a is 2 and b is 6. Now, the only thing that's left to do kind of at this point is to identify the function that we're dealing with. And so remember that when you look at the function, and if I come over here, that what we ended up doing was, sorry, I'm on the wrong color there, that this portion right here in this formula represents the right endpoint. And we're going to take out what was where that right endpoint is. So I'm going to take out this portion over here in the formula, and I'm going to replace it with x, because that's going to give me my function as a function of x. And so I'll highlight again right here. So then we can see that the stuff on the outside is what's representing the function that we are getting the area underneath. So there's the square root with the 5 and the minus 3. So we identify that. And so that's going to be my definite integral translated from the summation notation that you have. So that would be one example that we would do. Okay, now I've added a second example, and in this one we're going to work the other way, which is we are going to work from the integral, the definite integral, back to the summation notation. All right, so for this one, same thing that we were doing before. You're going to know that you're going to head toward a limit of a sum. So the limit as n goes to infinity, the sum I equals 1 to n. So that portion right there, you're really just putting in because you understand that the definite integral simply means you are doing the limit of a sum. So we add that in. The next thing that I do is I want to calculate my dx. So what we have and what we know that we're going to do is we're going to take this dx out and we're going to replace that with delta x. But that's going to require me to do a little bit of work. So delta x, if you remember, is b minus a over n. My b is 7. My a is 4. B minus a over n is going to end up giving me 3 over n. And so 3 over n is going to be what I am going to replace the dx portion with. So I'll put this down over here on this side. We'll move it out just a little bit so I have enough space. So my delta x is going to be this 3 over n. So that's what we're going to add that in for. All right, now the next thing that I need to do is I need to figure out my right endpoint. So do you see how I'm kind of working my way kind of methodically backwards? Now remember, my right endpoint is a plus delta x times I. So I have that formula down. My a in this problem is 4. Delta x is 3 over n times I. And so I know that that is what I'm going to replace the x in the function with. So it's now going to become e to the 3, and instead of that x, I'm going to replace it with 4 plus 3 over ni in that portion. And going back to my color coding, just so that we can have this very thorough, this x was replaced with the right endpoint. And then the function itself that we were looking at on this is the e to the 3x, and that was this portion right there. And so that's how you translate from the definite interval to the summation notation. Now, there's only one thing over here I did want to highlight, mostly because I don't really think you're going to see that on the AP exam, but I thought I would put it in there that you do have a different formula if you do the left endpoint. And the only difference is when you're doing the left endpoints is that when you look at, instead of I here, you have an I minus 1, because you don't want to, like for the first rectangle, you don't want to move over 1 times delta x. You really don't want to do anything for delta x because you want to start with the left one. So if you do that, I minus 1, all that really does is the first rectangle uses the left instead of the right endpoint. So I want to throw that out there just in case you might see something like that. But I will tell you the most common thing that I've seen is where they use the right endpoint. I've never actually seen them use the left endpoint. All right, for homework for this section then, and actually for the rest of this week, let me just show you what the things you're going to do. You're going to do your check your understanding for the set of class notes and watch the video for the homework discussion for that. The other thing that you're going to do is notice that here in the different handouts I have below here, I have several things from the College Board for you to practice. One is determining the type of approximation. So you're practicing on taking a look at definite intervals and their Riemann sum approximations, and then figuring out whether it was a left or a right or a midpoint. Now, I will tell you that in this kind of activity that we have going, that there is no requirement that your widths be equal widths. So I'm just going to put that out there as a hint to help you as you're working that. The second handout that you're going to work on is going to be one where we're matching definite intervals to the limits of Riemann sums, so kind of more practice of what we just finished. And then the third handout that I have here is going to be mind your P's and Q's. So again, more practice with trying to match the limit definition to the definite interval and why. So you're going to go through and you're going to work your way through that handout. And then the final thing that I have to kind of finish out this week, which is covering the 6.2, 6.3 in Unit 6, is we have a nice little circuit that we have where I would like you to, again, more practice with matching the summation limit to the definite interval and working your way through that. So that will finish out this week's lessons for the AP Calculus Unit 6. When you finish that, I'll start putting up probably toward the end of the week the videos for 6.4. And I'll tell you, this is the item coming up is the fundamental theorem of calculus. And anything that starts with the word fundamental is fundamental. So it's going to be something that's really important, our next little section that you have. All right, so that's going to end the part 2 video for class note 6.3, definite intervals as limits. And basically, y'all are going to be practicing for the rest of the week. Send me an email if you have any questions or any concerns about what we've covered so far.